All right, so this is page 331 from the textbook, number 27. So step 1, we factor out of 3. Once that 3 is factored out, hopefully you would see, oh, let's go ahead and divide both sides by 3. Okay, so let's do that. So if we divide both sides by 3, now we're left with this. And when we're looking at sine x equals 1 minus cosine x, you should think, well, I can't do anything when I've got sine and cosine. I need to get just one trig function. So if I change it into a reciprocal, that's not going to help, because that's still not going to be the same one. I can't use a Pythagorean identity because all my Pythagorean identities have squares in them, and these are not squares. So, can I factor? Nope, can't factor. When you've tried all those strategies, kind of your last resort, let's square both sides. So if I square both sides, this is what happens. Remember, this 1 minus cosine x has to go in parentheses. You're squaring the entire side. Now, just a note about notation. So up here, if I have sine x being squared, that is the same thing as sine squared x, right? So these are equivalent. It means the sine, you're squaring the whole function, you're not just squaring the x. These two mean the same thing. Because sine squared x, this is the way it looks on our formula chart. So right here, sine squared x, you can go, oh, that's a Pythagorean identity. So right here, you're going to do a substitution with a Pythagorean identity. So, substitution. I know I got some baseball players in here. You got a runner on first base. Maybe that runner sprained his ankle. He's going to come out and you're going to send in a pinch runner. It's going to come substitute. Going to go stand in the same spot he was standing in, right? And he is doing the equivalent job. He is a runner on first base. Substituting. You have a dollar bill and you need some quarters to put them in the arcade game. You're going to trade out your dollar bill for 4 quarters. An equivalent substitution. You're baking brownies and it says 1 cup of oil, but instead you put in 1 cup of applesauce. That's an equivalent substitution, and it makes your brownies taste better. No. So that's what we're doing here. We're substituting. It happens in lots of different arenas of our life, right? But it is just a matter of exchanging one quantity for another if the quantities are equivalent. All right. So now we've got 1 minus cosine squared x comes from the Pythagorean identity. And then here we've got to square this. So we're doing 1 minus cosine x times 1 minus cosine x. And we're multiplying that out, and we get here. Now at this point, we're going to add a -1 to both sides, and we're going to add a cosine squared x to both sides to set this side equal to 0. And now once we've gotten here, hopefully it will see that we can factor out a 2 cosine x. So right here we're going to factor. And that's going to give us 2 cosine x times the quantity cosine x minus 1. And now when 2 factors are being multiplied together to equal 0, that means that one of those 2 factors is 0. So either 2 cosine x is 0 or cosine x minus 1 is 0. So then we're going to solve those little baby equations. Cosine x is 0 or cosine x is 1. So we're thinking about our unit circle and we say, what angles has cosine equaling 0? Well, that's pi over 2 and 3 pi over 2. And what angle has cosine x equaling 1? And that's x equals 0. Because this problem said on the interval from 0 to 2 pi. That's what it said up at the top. But notice I have an x through 3 pi over 2. And sometimes when you're solving these, you get what we call extraneous solutions. And so you have to check and make sure they're actually true. And so, here's the checking part. If I plug in 3 pi over 2, right? Sine at 3 pi over 2 is -1, so I get -3 on the left-hand side. But cosine of 3 pi over 2 is 0, so I get 3 minus 0. I get positive 3 on the right-hand side. -3 and positive 3 are not equal. So even though I originally got this as a solution, I have to cross it out. It's called an extraneous solution. And when we do substitutions, and when we, especially comes in when you square both sides, sometimes extraneous solutions get introduced. So you have to check them. All right, so there was problem 27 as one example from your homework. If you did not do those problems, I strongly encourage you to go back this evening and catch up, because that means you're behind. All right, your quizzes. And again, I have not entered your guys' grades yet, but I do want to talk about the quiz. I want to talk about question 2. This is what question 2 said, and it said to simplify. So I want to show you that there's different methods, but I also want you to observe how I'm working. Every line is equal to the line above it. So I can change the order. That's called the commutative property. And I would do that so that sine squared x and cosine squared x are next to each other. So then when I add those together, those are equal to 1 by the Pythagorean identity. And then 1 plus tangent squared x is secant squared x by the other Pythagorean identity. That's probably the easiest, most efficient way to do that problem. It's not actually the first way that I thought of, right? When I made the answer key, I actually did it this way. My mind was reading left to right, and so the first thing I thought of was, if I change sine squared x to 1 minus cosine squared x, I can make these guys equal 0, and that's the way I thought of it. So I did that, so it's a Pythagorean identity substitution. And then you change the order around, and you add the negative cosine squared x with the positive cosine squared x, and that makes 0. So you still get to 1 plus tangent squared x, and that's secant squared x. That's another fine way to do it. But here's what some did. Some people started here. They replaced this with 1 minus cosine squared x, which was fine. But then the next thing they wrote down was cosine squared x, and then parentheses 1 minus 1 plus tangent squared x plus 1. And guys, that is, and then out of that they said that's secant squared x, and that's just flat out wrong. It's really important that you understand why this is wrong. And even if you're not the one who did it, if you're like, oh, Miss Collier, I know I remember I did it that other way. Learning from mistakes is a good thing. This says that cosine squared x is going to get multiplied by every term in here. Is it true that your cosine squared x is supposed to multiply with your tangent squared x? No. So that's why this is wrong. This is wrong. Now here's what I think these people were meaning to do. I think they were meaning to take the cosine squared x's and factor out a cosine squared x just from there and get 1 minus 1, which would then make this be 0, and then you'd have tangent squared x plus 1, and you'd have secant squared x. But even with this, would you not agree that this is a little off the beaten track way to do it? Like, why wouldn't you just add those together and get 0 instead of bothering to factor and then subtract and get 0? But sometimes we take a path that is a little different. But guys, when I have many people taking the same bizarre path, that tells me that we're not all doing authentic work, right? This is not a common mistake. This is like a really weird thing to do. So there's people copying either from each other or all copying from the same source. This solution could be on the internet. I don't know. Guys, you do realize that anybody can put stuff on the internet. Yes, Soren just said, be skeptical. If anybody can put it up, how do you know the person who put it up knows what the heck they're talking about? So if you copy a proof off the internet, it doesn't mean it's right. So I'm not quite sure where this got started or how it got spread around. Do your own work. Academic integrity is important. Just a word of warning, violations of academic integrity can be very harmful to your career. Valedictorians have been known to have their valedictorianship stripped from them for violations of academic integrity. You will not be in an honor society if you violate academic integrity. You certainly are not going to get good college recommendations written for you if you are one who violates academic integrity. Right? Do your own work. Your own work being done mediocre is better than copying someone else's work and turning it in as yours. Do not do that. All right. Enough of that. We are now going to look at sum and difference identities. So, take out your formula chart. To my connected learners, there are still some of these downstairs on the table. If you come to school for extracurricular activities, look on the table. They are on this bright yellow paper. They could be underneath some other papers by now, but they are still a bunch down there. I just looked the other day. Or print it out. But I really think having a hard copy is good as opposed to having to just switch tabs on your computer back and forth. We are going to be focusing on these right here, sum and difference identities. Please notice that there are 6 of them, 3 with a plus sign, those are your sum identities, and 3 with a minus sign, those are your difference identities. And you might look there and say, well, Miss Collier, there's something else weird about that. Like, that looks Greek to me. You're right, it is Greek. Let's talk about these variables for a minute. This guy right here is alpha. It is the first letter of the Greek alphabet. This guy right here is beta. It is the second letter of the Greek alphabet. Fun fact shared with me by Braden yesterday. When we talk about our alphabet, the word alphabet comes from alpha beta. Kind of cool, huh? So alpha and beta are typically used as variables to measure angles, just like the Greek alphabet of theta that we've been using. Okay? Now, some other books or resources might write out the sum identity like this. It might say cosine theta 1 plus theta 2. So sometimes you use subscripts to denote 2 different angles, whereas other resources will use the alpha and the beta to show that it's 2 different angles. Okay? So that's just a little background knowledge. Okay. Notice that we have cosine, sine, and tangent, all 3 trig functions represented. Take a look at your sines versus your sines that are on the right-hand side. Do you see that in cosine, the operation sign is the opposite, whereas in sine, the operation sign is the same. And in tangent, you have division, and you have the same operation on the numerator and the opposite operation on the denominator. But there's a lot of similarities, so you really have to pay attention to the symbols for adding, subtracting, and all that. All right, so let's do some examples. We're going to be working today both in degrees and in radians. Okay? So let's start with one on degrees. Sine of 75 degrees, and I would like to find the exact value. So let's talk about that, what that means, because I know some of you might say, oh, sine 75 degrees, that's so easy, Miss Collier. Pick up your calculator, and you go sine 75, enter. Look. Is that an exact answer?
No.
No. Your calculator has rounded this number, right? Sine of 75 degrees is really an irrational number, and the calculator has rounded it. This is not exact. So if you were to put this as your answer, that is not an exact answer. So how are we going to get exact answers? We need to use the unit circle. Okay? We need to use degrees that are on our unit circle. So look at the degrees that are on there. And what we have to do is we have to take the number 75 and we have to decompose it into two things on the unit circle being added together, or two values on the unit circle being subtracted. So, look at your degrees on your unit circle, right? And try and find a combination that adds to 75, and then try and find a combination that subtracts and gets 75. And once you have a combination, will you please type it in the chat? All right, so I'm seeing some answers being shared. Okay, so let's talk about these. 30 plus 45 does add up to 75. 30 is on our unit circle, 45 is on our unit circle, right? Okay, I'm working with sine. I can know the sine of 30 degrees. I can know the sine of 45 degrees. That's great. I see there 135 minus 60. 135 is on my unit circle. 60 is on my unit circle. If I subtract them, they do indeed equal 75. Alright, I see 315 minus 240. $315 is on my unit circle. 240 is on my unit circle. That is a difference of 75. That works. Alright, I see a 55 and a 20. Now, 55 and 20 does indeed equal 75. But that's not going to help us because those numbers are not on the unit circle, right? It has to be numbers that are on your unit circle. So this is not going to be helpful. It'll make total sense to you once we do one. All right, so let's let's take this suggestion to start with, the 30 plus the 45. So I'm going to say that the sine of 75 degrees is equivalent to the sine of 30 degrees plus 45 degrees. Right? Now, I've not done any trigonometry, right? I am just really breaking down a number, decomposing a number into two addends. 30 and 45 make 75. Now, we cannot just distribute this and say sine of 70 plus sine of 45. You can't distribute your sine function. But what you can do is use your sum identity. So, John, it works with numbers that are on the unit circle. So not just multiples of 5, we have to have multiples of 30 or multiples of 45.
Okay, yeah, sorry, I was like hearing you speak about it and thinking about how it probably has like a lot of like limitations in what it can be.
Yes. Alright, so I'm going to look at my formula chart and look for the sine that is the sum of two angles. And it says sine of first angle multiplied by cosine of second angle plus cosine of first angle multiplied by sine of second angle. So in this case, my alpha is 30 and my beta is 45. And I'm just going to substitute according to the identity. So it's sine of 30 degrees, cosine of 45 degrees. And you guys out of the remote, you can't see me. Like, I literally, over on the side, I have my little finger. I'm just following this formula, right? Plus cosine of 30 degrees, sine of 45 degrees. I've taken the sum identity and I've just plugged things in. But now we know the answers for each one of these pieces because they're on the unit circle. So you already have them memorized. And just in case you forgot them, they're on here. So, sine of 30 degrees. Sine of 30 degrees is 1/2. Cosine of 45 degrees. Cosine 45 degrees. Square root of 2 over 2. Cosine 30 degrees. 30 degrees cosine. Square root of 3 over 2. Sine of 45 degrees. 45 degrees sine. Square root of 2 over 2. Now we're going to multiply. Multiplying fractions, that's no problem. Top times top and bottom times bottom. Square root of 2 over 4 plus square root of 6 over 4. Yes, when you multiply with the radical, you can multiply the terms under the radical together. We have a common denominator, so add your numerators together. Done. This is an exact answer for sine of 75 degrees. Alright, just for kicks, somebody said we could do 315 minus 240. Let's do that just because. So sine of 75 degrees is also equal to sine of 315 minus 240. Again, this part has nothing to do with trigonometry. This is just number theory. 315 minus 240 is a way to be 75. Why did we pick these numbers? Because they're on our unit circle. Okay, this is a difference identity. It's got a minus sign. Go to your formula chart. The difference identity. Sine, cosine, minus cosine, sine. Sine 315, cosine 240, minus cosine 315, sine 240. Alright, unit circle time. Sine of 315. 315 is down here in my fourth quadrant. My fourth quadrant, remember, my sign is negative. Negative square root of 2 over 2. Alright, cosine of 240. 240 is over here in the third quadrant. Cosine is negative 1/2. Minus sign, because that's what the identity says. Cosine of 315. 315. Cosine, fourth quadrant, cosine, x value, cosine is positive. Square root 2 over 2. Sine of 240. 240 is over here. Third quadrant. And I'm on sine. Sine is negative. Square root of 3 over 3. Sorry, square root of 3 over 2. I misspoke. Negative times negative is a positive. Square root of 2 over 4. Negative times a negative. Positive. Square root of 6 over 4. Add your fractions. Common denominator. Ta-da! Same answer. Look at there. Now, something to think about. Isn't it easier to work with the first quadrant most of the time?
Yeah.
Like, I would imagine that you've got your first quadrant memorized better. Plus, in your first quadrant, sine and cosine are both positive, right? Don't have to worry about keeping track of negative signs. So, I would say if you can work with numbers in the first quadrant, probably an advantage. But, you know, perhaps if you just want to make your life more interesting, and sometimes you have to go to other quadrants, okay? And sometimes you don't. All right. Now, what if we have to do one that's in radians instead? So by this, I mean we're in radians instead of degrees. So before we even get into this problem, let's take a little sidestep because it's going to help you later. Look at all your radians. Pi over 6, pi over 4, pi over 3, pi over 2. If you needed a common denominator for all of those numbers, what would it be? 12. So being able to think in twelfths is going to be very helpful to you. So let us actually take a departure from this problem and make yourselves a little chart here of twelfths. Is pi over 12 on your unit circle? No, that's not going to help you. Is 2 pi over 12, what do you get when you simplify 2 pi over 12?
1 pi over 6.
Pi over 6. Is pi over 6 on your unit circle?
Yeah.
Yes, so this one is going to make you happy. That's going to be a good thing. Alright, what about 3 pi over 12? What does that simplify to? Pi over 4, right? Is pi over 4 on your unit circle? Yes, happy number. All right, 4 pi over 12 simplifies to divide by 4, divide by 4. Pi over 3, unit circle, happy, happy. What about 5 pi over 12? 5 pi over 12 doesn't simplify, not on our unit circle. Do not put anything with a 5 pi over 12. That's not going to help you. All right, 6 pi over 12, what does that simplify to? Divide by 6 over 6. Pi over 2, that's on the unit circle. All right, 7 pi over 12, is that going to help you? No. 8 pi over 12. Simplify your fraction. Divide by 4 over 4. 2 pi over 3. 2 pi over 3 on our unit circle. Happy, happy. 9 pi over 12. Divide by 3 over 3. 3 pi over 4 on the unit circle. Happy, happy. 10 pi over 12. Divide by 2 over 2. 5 pi over 6. Yes, it's on the unit circle. That's lovely. 11 pi over 12. No, not helpful. 12 pi over 12. That's pi, right? Is that on your unit circle? Yes. Okay? When you're dealing with radians, 12 is the least common denominator, so you're going to end up using twelfths a lot. And so, if you can think of your equivalent fractions, that's going to help. Alright. So, we got the cosine of negative pi over 12. Actually, you know what? Let's change this to be tangent. That's more exciting. Tangent of negative pi over 12. So the first thing I want to think about is, how can I get a pi over 12? Either adding two things together to get pi over 12, or subtracting two things to get pi over 12. What's a combination that would work to get negative pi over 12? If you have an idea, type it in the chat. Alright, so let's talk about some things. First of all, A+ for being risk takers and typing in the chat even if you're not sure of your answer. Okay? But if I do 2 pi minus pi, that's just going to leave me with pi. I'm trying to equal negative pi over 12, so that's not going to quite get there. If I do 9 pi over 12 and I take away 4 pi over 12, that's going to leave me with 5 pi over 12. I need a negative pi over 12. So I see a suggestion, pi over 4, take away pi over 3. 3 pi over 12, take away 4 pi over 12. Wouldn't that be a negative pi over 12? I'm just going to write it like this. 3 pi over 12, take away 4 pi over 12. Isn't that going to equal negative pi over 12? Ding, 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 ding. Alright, what if I did, because I think this is what somebody in there means. If I did 2 pi over 12 minus 3 pi over 12, it's got to be over 12, would that be negative pi over 12? Yes. So 3 pi over 12 is going to be pi over 4. 4 pi over 12 is going to be pi over 3. 2 pi over 12 is going to be pi over 6. 3 pi over 12 is going to be pi over 4. All right. So I'm going to show you where I'm going to choose the easier one before I get started. Look at my formula for tangent. Because I'm going to have subtraction, right? So I'm on tangent, a difference for tangent. So that's going to be tangent alpha minus tangent beta over 1 plus tangent alpha tangent beta. Okay, let me go back to our little chart that we made for tangent. Remember this little chart? Guys, if this is something and you wrote it like just kind of junky, all scribble scrabble in the corner of your, like, you might want to make yourself a really nice pretty one of this. If you were absent when we did this, you might want to take a screenshot or a photo right now. Look at my answers for tangent. Pi over 4, 1. Very nice number to have in our problem. Pi over 3, square root of 3. Very nice. Pi over 6. Yuck, a fraction. Do you see that then I'm going to have a fraction inside of a fraction? Do I really want to do pi over 6 if I don't have to? Pi over 3, nicer, right? So, let me go back to where I was writing, wherever that was. So, this is a perfectly good answer, right? But, and I could do it, but if I do this, I'll have pi over 6, and then my tangent answer is going to be a fraction, and then I'm going to have a complex fraction, and you guys know that that's just a pain in the neck. It's not hard, it's just cumbersome. So, because this is pi over 6, I'm going to say let's not go with that one, okay? So when you do these, you can save yourself a little bit of work if you think ahead. So let me come down here. Our original problem is tangent, negative pi over 12. We are saying, let's write that as tangent of 3 pi over 12, take away 4 pi over 12. Because, now I can come in here. This math just works, right? 3 pi over 12, take away 4 pi over 12 makes negative pi over 12. So it has nothing to do with trig, it's just fractions. Alright, but before I go to my identity, I'm going to simplify my fractions. That's going to be pi over 4 minus pi over 3. And some of you might think and be able to put this down to begin with, right? Now I go to my formula, my identity, as it's called. It says tangent alpha minus tangent beta divided by 1 plus tangent alpha tangent beta. So I literally put that over here on the side, put my finger on it, and do exactly what it says. Tangent pi over 4 minus tangent pi over 3 divided by 1 plus tangent pi over 4 times tangent pi over 3. I just become a little robot substituting. Alright, then I get my other chart, right? This is just all about having the right charts, isn't it? Tangent of pi over 4 is 1. Tangent of pi over 3 is square root of 3. 1 plus tangent of pi over 4 is 1. Tangent of pi over 3 is square root of 3. 1 minus the square root of 3 divided by 1 plus the square root of 3. When we're doing this work, we're going to go ahead and stop here. If we wanted to fully simplify, we would need to rationalize the denominator, right? But we're going to go ahead and stop right there, because we don't want to just focus all our energy on rationalizing.